In this video, we will learn about the inference about the two means for independent sample this time. So in the last videos, this last section was about section 9.4 about dependent sample in your textbook. But then this time we go back to section 9.3 and we'll learn about the independent sample. So recall from the last section, independent sample are the one that when you pick one value, then the next value won't depend on your previous value. For example, let's say if I want to see how much money do the people in California spend for the movie tickets each month comparing to the people living in New York, right? So when I pick one data randomly for one person in California, then I pick another one in California, and let's say I pick 30 samples, then the first person, when I pick the data, then the next one won't depend on the first person because I just randomly pick one of them. So these are the type of independent sample. And recall from the last section when I was talking about the dependent sample, let's say I want to check for the income of a family for the whole year, and if I pick one value, one data from a family of a female or a wife, then the next sample is must coming from the same family of the husband, because you want to take the value of the whole family. So after you pick the first value of the female or the male, then the next one should coming from the same family. So they are dependent, and we talk about that in the last example. And this time we will talk about independent sample. For dependent sample, we talk about the difference of the means, meaning that you're gonna subtract the two means from the two data together and then find the test statistic. But for this time, we keep them separately because they are independent. So the same requirement for independent sample, they must coming from the similar random sample. Again, they must be independent in this time, and there should be any no outliers. And make sure that the sample size are large, or n1 is bigger than or equal to 30. The same thing to n2. Two data, right? Two samples. Now, for the hypothesis testing, again, you must determine the null and alternative hypothesis. For the case of two-tail, the null hypothesis, in all these three cases, the two means are always equal to each other. Okay, they are always equal to each other. Now, for the two-tail, the alternative hypothesis would be that the mean one is different from the mean two, and the left tail is pointing to the left, or the mean one is less than the mean two, and the right tail is the mean one is bigger than the mean two, or the arrow is pointing to the right. Again, you are given this level of significant alpha. Now you compute the statistic, test statistic. Recall from the last section. Let's go back to the test statistic of the last section. Here, we take the difference of the means, or mu1 minus mu2, for the mu difference, right? But in this case, for independent, we keep them separately. So this is the mean for the first set of data. This is the mean for the second set of data. Okay. And the same thing for standard deviation. And you still have to draw the curve in order to compute the p-value correctly. For the TCDF, we're still using the lower bound, the upper bound, and the degree of freedom. And for the degree of freedom, because now we have two different data sets, the first one and the second one. For the degree of freedom, we need to pick the smaller of the two, n1 minus 1 or n2 minus 1. So which one gives you a smaller value, you pick that one. And again, if the p-value is less than the significant level, then you reject it, the null hypothesis. If your p-value is bigger than the level of significant alpha, then you do not reject the null hypothesis, which is saying that the two means are equal to each other. Alright, so let's go over the very first example for this section. So we are testing the hypothesis regarding the two means. Now, researchers wanted to know whether the state quarters had a weight that is more than the traditional quarters. So the state or the traditional quarter. He then randomly selected 18 state quarter and 16. So that this is 18 data, this is 16 traditional data, and he get the following data on the table here. Alpha is 0.05 in this case. Because we only have 18 and 16, they are all less than 30, which is this requirement. So they are less than 30. Therefore, we must construct a box plot to check for the whether the population is normal or not. But usually, as I told you, I will tell you that the data usually are normal, right? So you don't have to worry about that. Now, the null hypothesis. So let's first denote that the state quarter. We call this is the first data set, and the traditional quarter, this is the second data set. Now, this one is way more than the traditional quarter, which means this is bigger than, right, or pointing to the right, or the right tail. Now, the null hypothesis, it is always equal for the two mean. And for the right tail, we are testing whether mu1 is bigger than mu2. So we are checking this, whether we should accept this or we do not accept it. And for x1 and x2 bar here, they are the mean, the arithmetic means of the data. So x1 is when you add all of these numbers together and you divide by 18 because there are 18 data set, right? So x1 is when you add all of these numbers and you take the average by dividing by 18. You should guess that to be x1 bar is 5.702. And again, S1 is standard deviation. You can use the TI-8384 to calculate the standard deviation of that, the whole 18 data set, and this is found to be 0.0497. And for x2 bar, again, I add all of these numbers together. I divide by 16 because there are 16 number data, and I should guess 5.649. And then x2 is the standard deviation of that data set, and you can use the calculator to find a value to be 0.0689. Now, because the null hypothesis saying that mu1 and mu2 are equal, so when you subtract them here, mu1 and mu2 they are 0 because they are equal. So when you subtract them, they should be 0. Now let's see what the value we get here. So x1 bar is 5.702 minus 5.649 here, and then minus 0 because they are equal, so it should be 0. And then square root of s1 square, which is this one, and they are 18 for number 1, the stage quarter, and plus to the second one, 0.0689 square, and then 16, and that should get you around 2.537 if you do that correctly. Now for the degree of freedom, we have to take the smaller value of the two value here. So n1 is 18 minus 1 is 17, or 16 minus 1 is 15, so we take the smaller one of 15. So the p-value is going to be equal to TCDF. So let's draw the curve. We got the value 2.537. So it's a positive value, so let's say around here 2.537, right? And this is the right tail, so you want all the way up the right. So the lower bound is this one, 2.537, and you want all the way to the right, which is 10 to the 99, and the degree of freedom is 15. And doing that, you should get 0.0114, and this one is less than alpha, which is 0.05. So if p-value is less than the alpha, then you reject the null hypothesis. Right. So basically, you're gonna conclusion that you're gonna reject the null hypothesis. And the null hypothesis saying that the two mean are equal, so which is not correct, right? And we conclude that this one should be correct. So mu1 should be bigger than mu2. You reject the null hypothesis, meaning that mu1 should be bigger than mu2. Or the stage quarter should have a weight bigger than the traditional quarter. Okay, the next one is, the next objective is to construct the confidence interval for the independent mean. Again, if you go back to the last section for dependent, when we compute the confidence interval, again we're using the d, or the difference of the two data, but now we have independent data, so we have to keep them separately. Therefore, you can have x1 bar minus x2, which is the average of the data 1, data 2. The same thing for s1, s2, we found above here, right? And we have t alpha half. Okay, so again, you have to use the smaller between these two for the degree of freedom. So lower bound is this, and the upper bound is this one. The difference is the plus and the minus. Now let's try this example here. We want to construct a 95% confidence interval about the difference between the population mean, weight of a state quarter, and the traditional quarter. So we already discussed this in the last example. So now we're just gonna find the bound. We have all the data. So the bound is x1 bar minus x2 bar plus for the upper minus for the lower, t alpha over 2, and then s1 square and 1 plus s2 square and 2. We already found all the value of x1 bar, x2 bar, s1, and then s2, which is here, right? Which is here, the same thing, same example. But we don't have the value of t alpha over 2. Now alpha is what? Remember, this is 95%, so alpha is 1 minus 0.95 or 0.05. Then alpha over 2 is 0.025, and we're looking for t of alpha over 2 or t of 0.025, and this is just what the inverse t of 1 minus this, or 0.025. The degree of freedom is 15, the smaller one. Right, 15 here is the smaller n minus 1, and this should give you around 2.13. So after you plug in here, minus x2 bar plus or minus 2.13, you the same data from the last example. 18, this is 16. You should get for the lower bound using the minus, you should get 0.009, upper bound you the plus 0.097. Okay, so we are 95% confident that the difference between the states and the traditional quarter is between this and this, right? Between 0.009 and 0.097. Now, since the confidence interval does not contain the zero, because we are going from, this is 0 here, this is 0.009, this is 0.097, so the confidence interval is from 0.09 to 0.097. So in this region we do not include a 0, or does not contain a 0. We can conclude that the state quarter weigh more than the traditional quarter, because the null hypothesis saying that they are equal, right? They are equal. So if you move the mu2 to the left side, then you have the right tail to be bigger than 0. This is for the right tail. The last example was the right tail. From here, the right tail. Meaning that when you do the difference between them, you should have a value of bigger than 0, right? And in fact, the confidence interval here have all the values bigger than 0, and it does not include a 0. So yes, it's once again confirmed that the state quarter weighs more than the traditional quarter. So the confidence interval is another way to confirm the null hypothesis, or is not correct, or what we found here for the p-value is true, right? Or we reject the null hypothesis. Okay, so that is the end of this section for independent 9.3, and this is the extra stuff for your TI 384, and that's all. And the last one, we will talk about the inference about the two population standard deviation, which is the last topic of this chapter, and I'll talk about this in the next video.